Okay, so let's pick up where we left off. So we'll do example 2, 3 here. So it says, suppose the x velocity of a car at any time is given by the following equation. So we've got this. This is our first instance of having an acceleration that's not constant. So this is going to be a little bit different than we had in the AP Physics 1 class. So we've got our equation for the velocity, and they want us to find the change in the x component of the velocity of the car in the time interval 1 to 3 seconds. They want us to find the average x acceleration in that time interval, find the instantaneous acceleration by doing that same limit calculation, and then find a expression that'll give the exact instantaneous acceleration. So here's the thing to remember about this problem. This problem is identical to the problem we just did, except that we're talking about acceleration now instead of velocity. So if you take all those graphs we were looking at before and you do a velocity time graph instead of a position time graph, that's our difference. Okay, so now if I take a secant line, the slope of this secant line is average acceleration, and the slope of this tangent line is our instantaneous acceleration at that point, or like down here, this would be the instantaneous acceleration at that particular point. Okay, so let's take a look at this. So here's our function. So we're going to enter that function into the calculator. 60 plus 0.5 t squared. And then we'll go back to the home screen. And we need to evaluate it on the interval 1 to 3. So I'm actually we can reuse this entry up here since we changed y1. Go from 1 to 3. And so our average, our change in the x component of our velocity over that time interval is 4 meters per second. Now, if we want to find the average acceleration on that time interval, that means we need the change in the x velocity over the change in time. And so this is going to be 4.0 meters per second over 3 seconds minus 1 second. And so we'll get 2.0 meters per second squared as our unit. That's our average acceleration. We're going to do an estimate for our average acceleration, an estimate for our instantaneous acceleration at t equals 1 by taking progressively smaller intervals near t equals 1. We'll use our calculator for this again. We can actually reuse these entries from last time since we changed what y1 was. So this is, again, a technique that we can use to save ourselves a lot of time. So we get 1.05 meters per second. Meters per second squared. And then we'll do the next one. 1.005 meters per second squared. So we can see already that it appears to be approaching a value. Yep, and 1.0005 meters per second squared. So it looks like it's approaching the value 1. We could find an exact expression for the instantaneous acceleration in the x direction by taking the second derivative of the position function, or by taking the time-based derivative of the velocity function in the x which would be, now the derivative of 60, that's a constant, so that'll be 0. The derivative of t squared is 2t, so we're going to get 2 times 0.5 meters per second cubed times t. And again, you can see the units are going to come out right. So we have 1 meter per second cubed times t is our expression for the acceleration in the x. So definitely verified that the work we did in C was showing us the limit approaching the correct value of 1 meter per second squared. Okay, so let's talk a little bit about the kinematics equation. So with constant acceleration, you guys should remember these from AP Physics 1. We have our, again, if we have a constant acceleration, then this expression can tell us our final position based on initial velocity and acceleration, final velocity, and so on. Now, where did these come from? Well, we can use calculus to show where these equations came from. Now, in AP Physics 1, we did geometric arguments using graphs because calculus really isn't necessary, but just to get practice with calculus, we're going to do it this way this time. So let's say that our acceleration is a constant value, a. So here, a is just representing a number. It's not a function of time, so that's why that's not there. So no function of time, just a constant a. Now, we know that when we take the integral of something, we get the change in the value of the antiderivative. So here the antiderivative of the acceleration would be the velocity. So when we take the integral of the acceleration, we get the change in velocity. Another way to write change in velocity is v final minus v initial. And if we rearrange that, we get the equation we're familiar with. We could do this again. We could say, what about the change in displacement? Well, I can find displacement is the antiderivative of velocity. So if I take the integral of velocity, I'll get the change in position. And here's my velocity equation. So if I take the integral, I'm going to get, now the initial velocity is a constant. So I'm just going to get vi times t. And we're taking the integral with respect to t. So this is going to become t squared over 2 delta x. We can split that apart into x final and x initial, rearrange it, and get the equation we used in AP Physics 1. In this class, we're going to very often deal with problems where the acceleration is not constant. So if we need equations for velocity and position, we have to derive new formulas every time. The formulas that you're used to using from AP Physics 1 will not apply. We can't use them. So here's an example. Let's say that our acceleration is a function of time. We take the integral of the acceleration from 0 to t, and that gives us our change in velocity. We can split this apart into vf minus v initial and rearrange it, and we get this. So whatever our acceleration equation is, we need to take that integral from 0 to t, and I'm going to show you an example in just a second. If I wanted to find the change in position, then I need to take the integral from 0 to t of the velocity function with respect to time. So let's do this example here, or let's just look over this example here. So let's say my acceleration is a function of time. My acceleration changes as time progresses. And we need to know some initial values. We need to know where our particle is starting, and we need to know the velocity it starts at. So those are called our initial conditions, and we need those. So in order to find our change in velocity, we're going to take the integral of the acceleration with respect to time, and evaluating this, so t squared goes to t cubed over 3, t goes to t squared over 2, and this 1 goes to t. We're going to evaluate the whole thing from 0 to t. When we evaluate this, we're going to get all of this. When we plug in 0, this goes to 0, 0, 0. All of this is 0. What that means is when t is equal to 0, that's our initial condition. So 0, 0, 0, 0, our velocity initial should be whatever we said it was, 5 meters. So we've got 0 plus something has to equal 5. So that tells us that our initial velocity is 5 meters per second. So we plug that in as our initial velocity. If we want to find our position, we need to integrate everything again with respect to time. And let me just write that out explicitly here. So we're going to have our change in position is equal to the integral of the velocity with respect to time. And that's going to give us what we have down here. So we can rewrite this as, let me draw an arrow, not an equal sign. So we'll have the final position is equal to the integral from 0 to t of the velocity function plus the initial displacement. So again, we're going to take that integral here, and each of these terms we can see what's happening. T cubed over 3 is going to t to the 4th over 12, and so on. Again, when we plug in 0, that would be our initial displacement. So 0, 0, 0, 0 plus 20, or sorry, plus the, let me not skip a step here. So we've got 0 plus x initial is supposed to be equal to 25 meters, because that was our initial condition up here for the position. So we know that x initial has to be equal to 25, and that's what's happening there. So we plug in 25, and then this is our position function. This is our velocity function with respect to time, all based off of the acceleration equation we were given. We'll do more practice with this as we go on. And again, if you're just now starting calculus, some of this is not going to be very comfortable for you, just based on the fact that we barely touched this at the end of the pre-calc class. That's totally fine. Don't stress about it right now, but do your best to follow along with what we're doing.